Last day we talked about this total mechanical energy bucket, the combination of the kinetic energy and the gravitational potential energy buckets. And we said that it always stayed the same. That's what we meant by conservation. And yet there are lots of examples. I'll show you one right now where that kinetic energy bucket just drained right away. Now, if I call the level of the floor zero height, it never has any gravitational energy. So the kinetic energy is the total mechanical energy. I just had a situation where I had mechanical energy and I lost it. And you all know where it went. You heard it. Scraping going on. Right? And the friction was bleeding that energy out. It was robbing the system of that energy. And that's what we're going to talk about today, is how that energy changes. Now we're going to start with an example in which the energy doesn't decrease, but instead it increases. If I have a 15 kilogram block that's mounted on wheels, and these wheels are made of the very finest steel from the very finest factory in Sweden. It was built by a craftsman, Sven. Okay? And so the friction is negligible. So this little block is initially traveling at 5 meters per second. And then we push on it in the direction it's going for 10 meters. And we want to know how much did we fill up that kinetic energy bucket? How much did we change the kinetic energy? Now, I could solve that the old-fashioned way. I could calculate the initial kinetic energy, just 1/2 times 15 times 5 squared. And then I could use the kinematic equations to figure out how fast it's going after the push. And then I could calculate it again. But let me show you a better way. A way that will save you some time. Since we know that we never learn anything about time using energy, it makes sense that we start with the equation from kinematics that doesn't have time. And I'm going to just mess with that equation. It's not going to take long. It's not going to hurt. It's going to be very quick and painless. The first thing I'm going to do is I'm going to subtract off the V initial square. And that'll get it out of the right-hand side and put it on the left-hand side of the equal sign. Now I've left some real estate here and some real estate there. I'm going to use that real estate. The next thing I do is I recognize that net force is what causes a mass to accelerate. And that means the acceleration is that net force divided by the mass. If I replace the acceleration in this formula with the force over the mass, it looks like this. Now I'm going to use that real estate. I'm going to get that m out of the basement by multiplying both sides of the equation by m. I'm then going to get rid of that 2 on the right by dividing both sides of the equation by 2. And now, that looks like an old friend. And to you, it should look like a new friend. That's a kinetic energy. And what I have there is just the final kinetic energy minus the initial kinetic energy. Anytime I have final anything minus initial anything, that's the change. If we're talking about my change in weight over the holiday, over the break, it's my final weight minus my initial weight. That's how we find it. And that means that this thing over here is what causes the change. If this were 0, those guys would be the same. This is what causes the kinetic energy to change. And we call that, the force times the distance, we call it the Werk. Now I got to point out that we call it the Werk here in this classroom. Anywhere else in the world, they don't call it Werk, they call it work. But you people grew up in Montana doing work. You know work. And I'm here to tell you this physics Werk is nothing similar to what you did on the ranch. Okay, and we'll talk about that in just a moment. Now, the reason I call it Werk is just to remind you that it's different than everyday work. I kind of German it up. Now, I recognize that the actual word for work is Arbeit, and Arbeit macht frei, but this is close enough. This will get us down the road. We wanted to put it this way in the textbook, but the people that were reviewing the textbook thought that was just goofy. Okay? Now, if I look at that Werk, and I recognize that this is in newtons, and this is in meters, the units of Werk have to be Newton meters. Newton meters. What do we call that? A joule. And since the right-hand side of the equal sign has to have the same units as the left, that tells me that energy must have units of Newton meters or joules. Okay. Now, this Werk has a complication, and that is that it's not always positive. Now, to go back and solve this problem first, the easy way to solve it is to just say, hey, I have a 2 Newton force acting over 10 meters. That gives me a Werk, a positive Werk of 20 joules. That positive Werk is going to increase the kinetic energy bucket by 20 joules. That's the answer. That's the answer.